In this video, we build on what we talked about last time. That was the division algorithm, to discuss the structure of ideals in the polynomial ring k of x. So the coefficients of our polynomials lie in the field k, and these are polynomials in one variable x. What we're going to show is that all ideals in the polynomial ring of k of x, polynomials in one variable, can be written as an ideal generated by one polynomial function. In that case, we call the ideal a principal ideal. Any ideal that is generated by a single polynomial is called a principal ideal. And just as a reminder, the ideal generated by f is the set of all polynomials f times h, where h is any polynomial in the ring. So most of the time, as long as f is not the zero polynomial, this is infinitely many polynomials. And then after we show that that's true, we're going to show that if you have the ideal generated by the two polynomials f and g, it turns out that the single generator that corresponds to this ideal is the GCD of f and g, GCD being the greatest common divisor. So if you can find the greatest common divisor of f and g, you can find the single generator of the ideal generated by the original polynomials f and g. Now we have another term related to the fact that ideals generated by a single polynomial are called principal ideals. Since every ideal in the polynomial ring of polynomials in one variable is a principal ideal, so they can all be written in this way, so they're generated by a single polynomial, we say that the ring itself is a principal ideal domain, and we abbreviate that PID. So that's the plan. We're going to prove these two results. The first result is stated in corollary 4, and we're going to need some background on what an ideal is, and then it's helpful to just remember that the Hilbert basis theorem is coming. So corollary 4 says this: if k is a field, then every ideal in the polynomial ring, or polynomials are in one variable x, can be written in the form the ideal generated by f for some f in our ring. Furthermore, it says f is unique up to multiplication by a non-zero constant. And if you're not sure what that means, it just means that if the ideal generated by f and the ideal generated by g are equal to each other, then f and g have to be constant multiples of each other. They're almost the same, but they might be off by, say, multiplying by 2. If the first one is x, then g might be 2x, and they're going to give us exactly the same ideal. And before we prove this, it's helpful to review the definition of an ideal. We say that an ideal, or a set I, which is a subset of the polynomial ring in n variables, so our general polynomial ring, is an ideal if the following three characteristics are satisfied. If the zero polynomial is in the set I, and if f and g being an I implies the sum of f and g is an I, and if if f is an I and h is any polynomial in the ring, then h times f is an I. So that's the definition. And one thing that this definition doesn't tell you that we want to keep in mind is that every ideal can actually be written in this way. It is the ideal generated by a set of s polynomials, f sub 1 through f sub s. This is called the Hilbert basis theorem. We don't really have enough background yet to talk about or to derive this result, but this is proved in chapter 2. And if you're talking about an ideal generated by these polynomials f sub 1 through f sub s, that's just a set that satisfies all of this. The way you can think of this is that if f sub 1 through f sub s are all equal to 0, So we take all these polynomials, we set them equal to 0. The ideal is the set of polynomials that would have to be 0 if all of these polynomials are equal to 0. So we could take these polynomials, multiply them all by other polynomials in the ring, add them together. We're still going to get 0 because these are originally 0. Those polynomials that result from manipulating the equations associated with these polynomials, those polynomials are the polynomials in our ideal. Okay, so now let's use these two facts and our intuitive understanding of what an ideal is to prove the corollary. Okay, so if we have an ideal, and remember what our corollary says, every ideal in K of X. So this is not a general polynomial ring, but for a polynomial ring where our polynomials are polynomials in a single variable X, if we're dealing with that type of ideal, that's what our corollary is concerned with. Well, actually, this next fact is actually related to any kind of ideal in any polynomial ring, but we're going to stay here because that's where that's what we're concerned with the corollary. But given an ideal, either we have an ideal, containing a single polynomial, and that's the 0 polynomial, or we have an ideal that has infinitely many polynomials in it, and it's not equal to the set containing the 0 polynomial. Now, if you're not sure that this is true, let's think through this over here. If 0 is in I, well, that's satisfied. Well, if I is equal to the set containing the 0 polynomial, the first condition is satisfied. If there are any two polynomials in I, their sum is in I. Well, there are no two polynomials, but obviously 0 plus 0 is in I. And if you take any polynomial in I and you multiply it by h, that's going to be an I. Well, if there's only one polynomial in I, and that's z, 0 times h is 0, and of course 0 is still an I. So this satisfies the criteria for an ideal. So we're either going to be in this case or we're going to be in the more interesting case over here. Let's handle the interesting or the less interesting case first. Now remember, our corollary says that every ideal can be written in this form. Well, I claim that the ideal containing the 0 polynomial is the ideal generated by the 0 polynomial. The ideal generated by the 0 polynomial is the set of all polynomials, h times 0, where h is in our polynomial ring. Oops. And of course, that consists of just the 0 polynomial. And so that's I. So I can be written in this way. So the corollary holds when we're talking about this particular ideal. Now let's look at a more general case. Here's an ideal that does not consist of just the 0 polynomial. It's much more interesting than that. In that case, our ideal will contain infinitely many polynomials. So what we want to do is let f be a polynomial in I, and we want it to be a non-zero polynomial. So this I will contain the 0 polynomial, but we want one of the other ones. Oops. Need a little space there. And we want it to be a non-zero polynomial of minimal degree. So we want a polynomial in I of the smallest degree possible. Then our claim is that I is actually generated by that non-zero polynomial of minimal degree. In order to show that these two sets are equal, we're going to do the following. Our plan is to show that the ideal generated by the polynomial f is a subset of I, and I is a subset of the ideal generated by the polynomial f. If these two guys are subsets of each other, the only way that happens is if they're equal to each other. So first, let's show that the ideal generated by f is a subset of I. Well, first, in order to do that, we need to choose an element of this set. Then by definition, it's by definition of the ideal generated by f, g is going to equal to f times, or going to be equal to f times h for some h in our ring. But f is an element of I, because we said right here, f is an element of I, and it's a non-zero polynomial of minimal degree. Since f is an element of I, h times f is an element of I. So we started with a polynomial in this set, and we showed that it belonged to this set. So that shows us that this set is a subset of this set. Or in other words, every single polynomial in here is also in here. All right, let's go the other way. This time we want to start with a polynomial that is in our ideal. Well, since we said earlier that f was a non-zero polynomial of minimal degree in I, and g is also in I, then we know that the degree of f must be less than or equal to the degree of g. And if the degree of f is less than or equal to the degree of g, that means we could take g and we could divide it by f using the division algorithm. So g can be written as q times f plus r, where either r is equal to 0 or the degree of r is less than the degree of f by the division algorithm. And that's why we need the division algorithm in order to prove this result. Okay, so we know that this is true. Now, we already know that f is in I. Since f is in I and q is a polynomial in our ring, q times f is in I. That's because we're dealing with an ideal I, and q is some polynomial in the ring. That's just, again, a consequence of the fact that our ideal satisfies all three of these characteristics. Well, we know that that's true. And we also know that g is in I. So putting those two pieces together, we know that g is in I, and we know that q times f is in I. Then obviously we could multiply this by -1 and it would still be an I. And if we multiply this by -1 and we add it to that, what we get is the polynomial r. So we have r equals g minus q times f. since this is an I and this is an I, we can subtract those, and that will also be an I. Now, wait a minute. Do you see the problem? Look at what this said. This says that if G is some polynomial in I and F is in I, F is a non-zero polynomial of minimal degree, this is less than this. So this is true where R is either equal to 0 or the degree of R is less than the degree of F. But we have just shown through this argument here that if F is an I, then this is an I. And since G and F are an I, then R has to be an I. But we've already said that the degree of R has to be less than the degree of F. And that's a contradiction, because if R is an I and F is a polynomial of minimal degree, R can't exist. That's not possible. So we have a contradiction. Or we would have a contradiction if we didn't have this other possibility. The other possibility is that R is equal to 0. So let's actually write all of that down. So we have this, since R is equal to 0, or the degree of R must be less than the degree of F. And the second part is not true. Then we must have R equals 0. Well, if R equals 0, then we have G is equal to Q times F for some Q in our ring. And we wanted to show that if G is an I, then G has to be in this. Well, if G can be written as a polynomial times F, then G is clearly a member of this set. And since G being in this set implied that G was in this set, now we've got this conclusion. Oops. Okay, so first we showed that this was true, and then we showed that this was true. If one set is included in the other and the other way around is also holds, then they must both be equal to each other. Okay, so let's see, what did our corollary say? What were we trying to prove? We wanted to show that if K is a field, then every ideal in the polynomial ring consisting of polynomials in one variable can be written in this form for some F and K. And we did show that. We showed that if I is an ideal, then I can be written in this way. Either if I consists of the 0 polynomial only, I is equal to the ideal generated by the 0 polynomial, or I is equal to F, where F is a polynomial in I of minimal degree. We were able to show that. Now, the last part says, furthermore, F is unique up to multiplication by a non-zero constant. This is pretty easy to show. I don't think I'm going to show you uniqueness every time because it's a little easy, but it's good to see it a couple times, see it, the uniqueness proof basically and how it works. All you do for uniqueness is you assume that there are two of them and then show that they have to be equal to each other. Or in this case, we don't want to show that the two generators are equal to each other. We want to show that the generators are just constant multiples of each other, because we want F to be unique up to multiplication by a non-zero constant. If that's true, we want to show that that's true, and the corollary says that that's true. So if we want to prove uniqueness, we're going to suppose that two ideals are equal to each other. And our goal is to show that f and g are constant multiples of each other. Well, if these are equal to each other, then obviously they both contain the polynomials f and g. Because the ideal generated by f contains f, and the ideal generated by g contains g. And if they're equal to each other, then they both contain both. So that implies that f is in this ideal, and g is in this ideal. And what that means for us is that f is equal to h1 times g for some polynomial in our ring, and g is equal to h2 times f for some polynomial in our ring. Well, if you combine these two, then you can write it as an equation only, or involving only f. So if I take this top equation and I replace the g with what we have on the right-hand side of the bottom equation, we see that f is equal to this polynomial times f. Now, the only way that happens is if the product of those two polynomials is 1. Now, if we're talking about polynomials, if this has any x's in it, well, we can't have 1 over a polynomial over here and still be in the polynomial ring. The only way that I can take a polynomial, multiply it by a polynomial and get 1 is if both of those are constants and they're not, well, they may or may not be equal to each other, but they can't have any x's in them. So if this is true, then h1 must equal some constant. Let's say it's c, and that's going to be in our ring K. And h2 must be 1 over c. That's for some c and k. And since h2 is just a constant, we've just shown that g has to be a constant multiple of f. And that's the same as saying that the generator f is unique up to multiplication by a non-zero constant. So if this one is x squared plus 1, this one could be x squared plus 1, that whole quantity times 3, and that would totally be fine. You get exactly the same ideal. All right, so that is our corollary, and you can see why the division algorithm is important. The division algorithm allows us to state this relationship. And this relationship, combined with the fact that f was a non-zero polynomial of minimal degree in I, was what allowed us to show that r was equal to 0, because this was true or this was true, and this could not be true while the first part was true. So r would have to be 0, and if r is 0, that means that g is in the ideal generated by f. Okay, so that was our first result. Now, we know that every ideal is generated by a single polynomial, but it's kind of hard to find it. Remember what that proof just suggested? It's saying that, oh, if you have an ideal, it's generated by a non-zero polynomial of minimal degree. Just find that. Well, if you have an ideal which is made up of infinitely many polynomials, remember You take the non-zero polynomial of minimal degree and you multiply them by all the other possible polynomials that are out there. And those are the polynomials in your ideal. You've got infinitely many of them if f is not the zero polynomial. It's kind of hard to sort through that list of infinitely many polynomials and find the one of smallest degree. You might be saying to yourself, how do I find that? It turns out you can find that using something called the Euclidean algorithm. And it turns out that the Euclidean algorithm well, it's not that the Euclidean algorithm will show us this, but we will see that the generator for a polynomial ring defined by polynomials f sub 1 through f sub s is the greatest common divisor of f sub 1 through f sub s. So I'm kind of giving it away. Okay. How do we find it? Well, what we do is we find the greatest common divisor. In order to talk about that, let's define the greatest common divisor, or a greatest common divisor. A greatest common divisor of two polynomials f and g in the ring where our polynomials are all in one variable is a polynomial h that satisfies the following. First of all, h divides g and f, or f and g if you prefer to go alphabetical. Or in other words, h is equal to, sorry about that, let's go the other way. F is equal to h times h1, and g is equal to h times h2, where h1 and h2 are polynomials in our ring. So another way to say this, instead of saying greatest common divisor, you might prefer to say greatest common factor. So we say GCD So h is the largest factor that f and g have in common. Okay, so we said a greatest common divisor of f and g is a polynomial that satisfies this. First of all, it divides f and it divides g. That means it's a common factor. But in order for it to be the greatest common factor, the second part of this must hold. If p is another polynomial which divides f and g, then p divides h. So we're saying that h is the largest factor that these guys have in common. So this is saying, well, what if p is some other polynomial that divides those? So what if p is some other polynomial that satisfies a relationship like this? P is a factor of f and p is a factor of g. I still tend to think in terms of factors instead of divisors. So I tend to use the GCF language as opposed to the GCD language, although the GCD language is what we use in our text. So if p is a factor of f and g, this is saying that p has to be a factor of h, because h is the largest factor that f and g have in common. So that is our definition. Let's look at a concrete example. Again, it's just a little pre-calculus example, easy breezy. Whenever we look at our pre-calculus example, it makes something that seems a little bit of abstract more concrete, and then because it's concrete, then the proof will make a little bit more sense, hopefully. Well, this is actually just a definition, but the proof of the next proposition will hopefully make more sense. And then we've got some new notation. We write this, say that h is equal to the GCD of f and g. So just for example, let's say you've got a polynomial that is given by x minus 2 squared times h, or x plus 3 times x minus 4, and you have another polynomial g, which is x minus 2 times x plus 3 times x minus 4. Or not x minus 4, let's make that last one x minus 5, let's say cubed. Okay, the greatest common divisor, h, of these two guys is the largest factor that they have in common. So if I'm looking for the greatest common divisor, I say, well, what factors do they have in common? Well, they both have an x plus 3 in common, so I can write that down. And do they have an x plus 4 or x minus 4 in common? No. Do they have an x minus 5 in common? No. G has x minus 5s as factors, but this one doesn't. Do they have an x minus 2 in common? Yes. So I'll write that down. Do they have two x minus 2s in common? No. This one has two factors like that, but that one only has one. So h is equal to this. And one way that you can show that these functions can be written in this form is to say, well, what is f? F is equal to h, which is x plus 3 times x minus 2 times some other polynomial. Well, what else? What's missing in order to create this? Well, I need another x minus 2, and I need the x minus 4. So this is the h1 that we have up there. And of course, this is h. Similarly for g, g is equal to x plus 3 times x minus 2. That's our h. Of course, it's written in a different order, but that's okay because multiplication is commutative, right? And then the rest is this x minus 5 cubed. That's our h2 for that relationship right there. And if you're saying to yourself, how do you know that that's the greatest common factor? It's obviously a common factor because h is on this list and h is on this list, but how do you know it's the greatest? You just look at the rest of the factors and you see that there is no overlap. X minus 2 times x minus 4, neither of those factors is on this list. This is just 3 x minus 5s. X minus 5 times x minus 5 times x minus 5. There's nothing in common for these guys and these guys. If there was still something in common, then this would not be the greatest common factor. It would just be a common factor. So that is the GCD. Now the second criterion is that if P is another polynomial which divides both F and G, then P divides H. Well, yeah, I think that that's true. If P divides these guys, well, it can't divide Well, if it divides both of these, it has to divide it has to divide this or this, because these guys don't have anything in common. So other polynomials that divide f and g are x plus 3 and x minus 2. But if you want the greatest common divisor, or the greatest common factor, you need to multiply those two together. Okay, so that little pre-calculus aside hopefully helps us to understand what the GCD is a little bit better before we look at the next proposition. So here's proposition 6. Proposition 6 says that if f and g are in our polynomial ring, then first of all, the GCD of f and g exists, meaning it exists in the ring and is unique, again, up to multiplication by a non-zero constant in k. Obviously, I could multiply h by 2 here, and that would be fine, as long as I also multiplied those by 1/2. Okay. Well, actually, well, yeah, that'd be fine. And then the next part is this, GCD, the GCD of f and g, if we call that h. This is the generator, or is a generator of the ideal generated by f and g. In other words, this is a principal ideal domain. So every ideal can be written as an ideal generated by a single polynomial. That single polynomial is the GCD. And then the third point in this proposition is that there's an algorithm for finding this. That's called the Euclidean algorithm, and we're actually not going to do that in this video. We'll do that in the next video. But before we go, let's look at proposition 6, and let's prove that the first two pieces are true. Okay. First, we just want to show that the GCD exists. So in order to show that first part, let's do the following. Let's consider the ideal generated by the polynomials f and g. Now we've already proven that k of x is a principal ideal domain. So since we know that that's true, we know that this ideal can be written as this for some polynomial h in our ring. Our claim is that h is the GCD. Okay. Now, if you want to prove that h is the GCD of these two guys, where this ideal is equal to this ideal, we want to use the fact that these two are equal to each other to show that H has to satisfy these two parts of the definition. So we want to use our assumption here to show that H divides F and G, and that if P is any other polynomial which divides F and G, P has to divide H. So that's the goal, that's the plan, and that's what's necessary if we want to show that H is actually equal to this thing. So we know that these two are equal to each other, these two ideals are equal to each other. And if these two ideals are equal to each other, then obviously F and G belong to this ideal and H belongs to this ideal. And if they're equal to each other, F, G, and H belong to all of them. So what we can say from here is that what I'm most interested in is this. F and G have to be in this ideal over here. And if F and G are in this ideal, remember what that means. That's the same as saying that F is equal to H times H1, where H1 is in our ring. And G is equal to H times H2, where H2 is in our ring. That's the same as saying that F and G are divisible by H, or H divides F and G. So that first part of our definition of the GCD is satisfied. Now, if you're going through this and you're like, okay, I think that that's pretty obvious. When I see F, I see that F and G are members of this ideal generated by H. I immediately know that F and G are divisible by H, or that H divides those. Like, this implies this to me, and I don't have to show this step. That's awesome. If you are in that category and you can see that this goes directly here, then that's great. I'm just including this for those people that don't see it immediately. So keep that in mind as we go through this. I'm trying to make this video so that it's helpful for everyone. Okay, so our first requirement is satisfied. And now we want to show that if P also divides F and G, then P must divide H. Now I'm going to use exactly the same notation that they used in the book, just to make it clear and easy to refer back and forth from the book to these notes. So we're saying that P divides F and G, so that means that F is equal to C times P and G is equal to D times P for some polynomials C, D in our ring. Now, we already know that these two guys are equal. And since these two guys are equal, not only are F and G in this ideal, H has to be in this ideal. And if H is in this ideal, that's the same as saying that H is equal to some polynomial times F plus some polynomial times G. Where A and B are in our ring. Now we could have used H1 and H2. We're just choosing to use these capital letters A, B, C, and D because that's what they used in the book. And I think the reason they did that was because they didn't want too many H's floating around. So we've got this. So H is equal to this. Well, and F is equal to C times P, and G is equal to D times P. So we can substitute those here. F is CP. According to this, G is D times P. And of course, you can factor out P from this term and this term. I'm using the term loosely. Expression separated by a plus addition sign. And since A, C, B, and D are polynomials, this is a polynomial times P. And of course, the polynomial is also in the ring. So H is equal to this polynomial times P. So that means that P divides H. So both requirement 1 and requirement 2 for the GCD is satisfied. So that means that H is equal to the GCD of F and G. And we've also shown that H is the generator of the ideal generated by F and G. It is one of the generators of this ideal. And all the other generators of this ideal, if you were to just require that you were dealing with a principal version of that ideal so that you only have one basis function over here, they're all going to be multiples of this GCD. And I guess I should say that it is a generator, not the generator. But it's the generator up to multiplication by a non-zero constant. Now for uniqueness. I show this. This is the only one. Let's say that you have another H. I'm going to call it H prime. And that's also equal to the GCD of F and G. That prime is not a derivative. It's just a different H. Okay, since H prime is a GCD and H is a GCD, that means that both of those divide both F and G. And if there's any other, if there's any other factor or any other polynomial which divides F and G, that polynomial divides both H and H prime. So if you've got two GCDs, they have to divide each other. And if they divide each other, I think it's pretty obvious that they would have to be non-zero constant multiples of each other. And that's coming from the second requirement in our definition of the GCD. So H is divisible by H prime and H prime is divisible by H. Okay, so now we know the structure of ideals in our polynomial ring. We know that if we are in a ring of polynomials in one variable, all ideals can be written in this form. And if you're trying to find the generator or a generator for a particular ideal, and that ideal was originally given by this basis, the basis with two polynomials F and G in it, all you have to do is find the GCD of those two polynomials. The GCD of those two polynomials will be the ideal that generates this ideal over here. Now, in the next video, we're actually going to talk about how we find the GCD. So what we have just shown is that it exists and it's unique up to multiplication by a a constant. But we haven't actually given you a way to find it. I'm going to give it away a little bit. We're going to find the GCD using another algorithm, and this is called the Euclidean algorithm. And then we're going to extend what we've said about ideals generated by two functions f and g to ideals generated by s functions, f sub 1 through f sub s. It turns out that if you have an ideal generated by f sub 1 through f sub s, the polynomial or a polynomial generator of that is just the GCD of all of these guys. So we're going to talk about how we find that GCD when you have two functions, and then we're going to talk about how to extend what we've already talked about to s functions rather than just the two functions.